Hello, and welcome to the Cozy Curiosity channel. Tonight, we'll embark on a tranquil journey through the atmosphere, exploring 100 mind-blowing facts about weather, the invisible forces that shape our daily lives, paint our skies, and carve our landscapes. From gentle morning mists that blanket quiet valleys, to powerful storms that span entire continents, weather touches every moment of our existence in ways both subtle and profound. So before you get comfortable, take a moment to like the video and subscribe. It helps other sleepy souls find their way here. And let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. Now settle in, breathe deeply, and let your mind drift like clouds across an endless sky as we uncover the beautiful science behind rain, wind, lightning, and everything in between. Whether you're here to relax, learn, or simply fall asleep to the gentle rhythm of knowledge, these calming stories and fascinating truths will carry you peacefully through the night. Let's begin. Lightning strikes Earth approximately 100 times every single second. As you lie here in the comfort of your quiet space, it's almost impossible to imagine that at this very moment, somewhere on our planet, lightning is tearing through the sky. Not just once or twice, but roughly 100 times every second, creating a continuous global light show that never stops. This means that about 8.6 million lightning strikes occur every single day across Earth's atmosphere. These brilliant electrical discharges happen when ice crystals in storm clouds collide and create a separation of positive and negative charges, building up tremendous electrical potential. When the voltage difference becomes too great, the atmosphere can no longer insulate the charges from each other, and a massive spark leaps through the air, briefly heating the channel to temperatures hotter than the surface of the sun. Most of these strikes occur over land rather than ocean, and tropical regions experience far more lightning than polar areas because of the stronger convection currents created by intense heating. This endless electrical symphony reminds us that Earth's atmosphere is constantly alive with energy, reshaping molecules, fixing nitrogen into soil, and creating the rumbling thunder that has echoed across countless human generations. A single thunderstorm cloud can weigh more than 1 million pounds. When you gaze up at a fluffy cumulus cloud drifting lazily across a summer sky, it's easy to think of it as light and airy, almost weightless. But the reality is far more astonishing. A typical cumulus cloud, despite appearing delicate and ethereal, contains roughly 500,000 pounds of water suspended in tiny droplets throughout its massive volume. Larger storm clouds, the towering cumulonimbus formations that spawn thunder and lightning, can contain over 1 million pounds of water. To put this in perspective, that's equivalent to the weight of several hundred elephants floating above your head. These enormous masses stay aloft because the water exists as countless tiny droplets, each so small that air resistance keeps them from falling, and because the cloud sits atop powerful updrafts of warm air that continuously lift moisture upward. The water droplets are so small, typically between 10 and 20 micrometers in diameter, that it would take millions of them to form a single raindrop. As the cloud matures and droplets collide and merge, they eventually become heavy enough to overcome the updrafts, and rain begins to fall. This delicate balance between gravity pulling down and air currents pushing up creates the dynamic, ever-changing sculptures we see painted across our skies, each one a temporary masterpiece, weighing more than the largest vehicles we build. Some raindrops are shaped like hamburger buns, not teardrops. From childhood, we're taught that raindrops look like tears, with a pointed top and rounded bottom. But this common image is actually incorrect. Real raindrops in free fall through the atmosphere are shaped more like hamburger buns or slightly squashed spheres. Small raindrops, less than about 2 millimeters in diameter, are nearly perfect spheres held together by surface tension, that invisible skin that forms at the boundary between water and air. As raindrops grow larger by colliding with other droplets, air resistance begins to deform them. The bottom flattens out because air pressure pushes against it as the drop falls, while the top remains relatively rounded. Very large raindrops, those approaching 5 or 6 millimeters in diameter, become so distorted that they're almost parachute-shaped, with a large flattened bottom and a rounded or slightly concave top. Eventually, if a raindrop grows too large, it becomes unstable and breaks apart into smaller droplets. This typically happens around 6 millimeters because the air pressure and turbulence overwhelm the water's surface tension. Terminal velocity for most raindrops ranges from about 7 to 20 miles per hour, depending on size, which is much slower than you might expect. Understanding the true shape of raindrops helps meteorologists improve weather radar accuracy and climate models, showing us once again how careful observation reveals the unexpected beauty hidden in everyday phenomena. Earth's atmosphere weighs approximately 5.5 quadrillion tons. The air surrounding us feels weightless as we move through it, invisible and seemingly insubstantial. Yet the total mass of Earth's atmosphere is almost incomprehensibly heavy. If you could somehow gather all the air from the surface to the edge of space and weigh it, the scale would read about 5.5 quadrillion tons, or 5,500 trillion metric tons. This enormous mass creates pressure at sea level, pressing down on every surface with a force of about 15.7 pounds per square inch. We don't feel this crushing weight because our bodies and the air inside us push back with equal force, creating a perfect balance. The atmosphere extends hundreds of miles above Earth's surface, but about 75% of its mass is concentrated in the lowest 7 miles, the troposphere where all our weather occurs. As you climb higher, air becomes thinner and lighter because there's less atmosphere above pushing down. This vast ocean of gas is held in place by Earth's gravity, prevented from escaping into space, and it's constantly churning and mixing as temperature differences create winds and weather patterns. Every breath you take connects you to this massive envelope of air, a protective blanket that shields us from harmful radiation, burns up meteors, and maintains the narrow temperature range that makes life possible on our planet's surface. Snowflakes can take up to an hour to fall from cloud to ground. There's something profoundly peaceful about watching snow fall gently from a grey winter sky, each flake drifting downward in its own unique path, caught occasionally by small eddies and currents of air. What seems like a direct journey is actually an extended voyage through the atmosphere. Depending on the cloud height and atmospheric conditions, a single snowflake can take anywhere from a few minutes to over an hour to complete its descent from cloud to ground. The terminal velocity of a snowflake, the fastest speed it can fall, is surprisingly slow, typically between 1 to 4 feet per second, or roughly 1 to 3 miles per hour. This leisurely pace results from the snowflake's intricate crystalline structure, which creates a large surface area relative to its tiny mass, generating significant air resistance. As the snowflake tumbles and spins through varying temperature and humidity zones on its journey downward, it continues to grow and change shape, adding new ice crystals to its structure. In calm conditions with light winds, the descent might be fairly direct, but in turbulent air, a snowflake might actually rise and fall multiple times before finally reaching the surface. This extended journey through the sky is why snowflakes from the same cloud can look quite different from each other, each one recording a unique history of temperature and moisture conditions encountered during its long, spiraling fall to Earth. The smell before rain is caused by a compound called petrichor. There's something deeply comforting about the earthy, almost sweet smell that fills the air just before or right after a rainstorm. A scent that seems to awaken something primal in our memories. This distinctive aroma has a name, petrichor, derived from Greek words meaning stone, and the fluid that flows in the veins of the gods. The smell actually comes from several sources working together. During dry periods, certain plants release oils that coat nearby rocks and soil. When rain falls, these oils are released into the air, along with a compound called geosmin, produced by soil-dwelling bacteria called actinomycetes. Geosmin is an organic compound that the human nose is remarkably sensitive to, able to detect it at concentrations as low as 5 parts per trillion. Another contributor to that pre-rain smell is ozone, which can be carried down from higher altitudes by storm downdrafts, giving the air a sharp, clean scent. The rain itself helps by creating tiny air bubbles as droplets hit the ground. When these bubbles pop, they launch aerosols containing these aromatic compounds into the air we breathe. This complex symphony of scents served an important evolutionary purpose, potentially helping our ancestors predict incoming rain and plan accordingly, a gift from nature that still brings comfort and nostalgia with every summer storm. Psst. Wind doesn't actually blow in straight lines, but in spiraling patterns. When we think of wind, we often imagine it as a straight-line movement of air from one place to another, perhaps rippling across a field of wheat or whistling through city streets. However, the reality of how air moves across our planet is far more complex and beautiful. Because Earth is spinning on its axis, an effect called the Coriolis force causes moving air to deflect to the right in the northern hemisphere and to the left in the southern hemisphere. This means that winds flow in curved paths, creating spiraling patterns around high and low pressure systems, rather than blowing directly from high to low pressure, as you might expect. In the northern hemisphere, air spirals counterclockwise around low pressure systems and clockwise around high pressure systems, while the opposite occurs south of the equator. This spiraling motion is why hurricanes and cyclones have their characteristic rotating structure, and it's why weather systems don't simply rush in a straight line across the globe, but follow swooping, curved trajectories. At smaller scales, local geography creates even more complex wind patterns as air flows over mountains, through valleys, and around buildings, generating eddies, updrafts, and downdrafts. These invisible rivers of air carry seeds, dust, moisture, heat, and even insects and birds thousands of miles from their origin, connecting distant ecosystems and shaping climates across entire continents in an endless swirling dance driven by temperature differences and our planet's rotation. The largest hailstone ever recorded in the US was 8 inches in diameter. Imagine holding a sphere of ice nearly the size of a volleyball, heavy and cold in your hands, knowing it fell from the sky. In 2010, in Vivian, South Dakota, Such a hailstone crashed to Earth during a severe thunderstorm, measuring 8 inches in diameter and weighing just under 2 pounds. This monster hailstone became the largest ever officially measured in the United States, though locals reported seeing even larger stones that broke apart on impact. Hailstones form inside powerful thunderstorms, where strong updrafts repeatedly carry ice particles up into extremely cold regions of the cloud. Each trip through these sub-freezing zones adds a new layer of ice, like an onion building up rings. If you were to cut a large hailstone in half, you'd see these concentric layers, each one representing a journey through different parts of the storm cloud. The size a hailstone can reach depends on how long these updrafts can keep it aloft against gravity's pull. Inside a supercell thunderstorm, updrafts can exceed 100 miles per hour, strong enough to suspend remarkably large chunks of ice for extended periods. Eventually, the hailstone becomes too heavy, even for these powerful winds, or gets caught in a downdraft and plummets to Earth. Large hailstones like this can fall at speeds exceeding 100 miles per hour, carrying enough energy to shatter windows, dent cars, and devastate crops. The formation of such massive hail requires an extraordinary combination of atmospheric instability, moisture, and powerful convection, making these ice giants relatively rare but unforgettable reminders of the raw power contained within thunderstorms. Fog is simply a cloud that has touched the ground. On a misty morning, when you step outside and find yourself enveloped in soft grey moisture that limits visibility to just a few dozen feet, you're actually walking through a cloud. There's no fundamental difference between fog and clouds floating thousands of feet above. Both are composed of tiny water droplets or ice crystals suspended in air, each droplet so small that it remains airborne, scattering light and creating that characteristic white or grey appearance. Fog forms when air near the ground cools to its dew point, the temperature at which water vapor condenses into liquid droplets. This can happen in several ways. When warm, moist air moves over a cold surface like snow-covered ground or cold ocean water. When air cools by radiating heat away on a clear, calm night. Or when rain falls through cool air near the surface. Different types of fog have their own character and formation mechanisms. The fastest temperature drop ever recorded was 49 degrees in just 2 minutes. Weather can change with remarkable speed, but few events demonstrate this more dramatically than what occurred in Rapid City, South Dakota, on January 10, 1911. At 7:30 in the morning, the temperature read a relatively mild 55 degrees Fahrenheit. Just 2 minutes later, at 7:32, thermometers had plunged to 6 degrees Fahrenheit, a jaw-dropping drop of 49 degrees in 120 seconds. This extraordinary event was caused by a powerful Arctic cold front sweeping across the region, bringing frigid air masses that had originated far to the north. The front acted like an invisible wall, dramatically separating warm and cold air masses. As it passed through Rapid City, it replaced the mild air with bitter Arctic air almost instantaneously. Such extreme changes happen occasionally in locations where geography and atmospheric conditions align perfectly. The Great Plains of North America are particularly susceptible because there are no significant east-west mountain ranges to slow the movement of air masses, allowing cold Arctic air to rush southward unimpeded. These rapid temperature swings can be dangerous, catching people unprepared and sometimes leading to hypothermia or frostbite. They can also cause infrastructure problems as materials expand and contract rapidly, potentially cracking roads. damaging buildings and stressing power lines. This record-breaking temperature drop reminds us that the atmosphere is constantly in motion, with vast rivers of air at different temperatures flowing across the planet, occasionally colliding with spectacular and sometimes unsettling results. Rainbows are actually complete circles, not arches. When a rainbow appears after a storm, stretching across the sky in brilliant bands of color, we almost always see it as an arch, a half circle of light rising from the horizon. But this is only part of the story. Rainbows are actually complete circles of colored light, and the reason we typically see only an arc is simply because the ground blocks the bottom half from our view. Each raindrop in the air acts as a tiny prism, refracting and reflecting sunlight. When sunlight enters a raindrop, it slows down and bends, separates into its component colors because different wavelengths bend by different amounts, then reflects off the back of the drop and exits, bending again. This double refraction and single reflection create the primary rainbow, with red on the outside and violet on the inside. For you to see a rainbow, the sun must be behind you, and water droplets must be in front of you, and the geometry must be just right. Specifically, the angle between the sun, your eye, and the rainbow is always about 42 degrees. If you could get high enough above the ground, say in an airplane or on a mountaintop, looking down at rain below, you'd be able to see the rainbow's full circular shape. Pilots often witness complete circular rainbows, sometimes even with their plane's shadow visible at the center of the ring. Some rainbows appear doubled, with a secondary, fainter rainbow visible above the primary one, created by light reflecting twice inside each raindrop. In the secondary rainbow, the colors appear reversed, with violet on top and red on bottom, and the sky between the two rainbows appears noticeably darker, a region called Alexander's band. Every rainbow is unique to the observer seeing it, positioned precisely around the anti-solar point, the spot directly opposite the sun from your perspective. Moonlight can create rainbows at night, called moonbows. Most of us have never seen a moonbow, and many people don't even know they exist. But these rare and ethereal phenomena occur under specific conditions when moonlight, rather than sunlight, creates a rainbow. Moonbows form through exactly the same physical process as regular rainbows, light refracting through water droplets. But because moonlight is much dimmer than sunlight, moonbows are correspondingly fainter and harder to see. To human eyes, moonbows often appear as pale, ghostly arcs with little to no visible color, because the light is too dim to activate the color-detecting cone cells in our retinas, though long exposure photography can capture their full spectrum. For a moonbow to appear, several conditions must align. The moon must be fairly bright, typically full or nearly full. It must be relatively low in the sky, usually less than 42 degrees above the horizon. The sky must be dark, so moonbows only appear at night, and there must be water droplets in the air opposite the moon, from rain, spray from waterfalls, or mist. Some locations are famous for moonbow sightings, particularly areas near large waterfalls where mist is consistently present. Cumberland Falls in Kentucky, Victoria Falls in Africa, and Yosemite Falls in California are all known for producing moonbows on full moon nights when conditions are right. Witnessing a moonbow is a magical experience, a delicate silver arc glowing softly against the darkness, a reminder that even in night's shadows, the physics of light and water continue their ancient dance. Dust from the Sahara Desert regularly crosses the Atlantic Ocean. It seems impossible that fine particles of sand and dust from Africa could travel thousands of miles across an entire ocean. Yet this remarkable journey happens regularly, sometimes multiple times each year. Strong winds over the Sahara Desert lift millions of tons of fine dust particles high into the atmosphere, where they catch rides on prevailing wind patterns, particularly the trade winds that blow from east to west. These dust plumes can be massive, sometimes covering areas larger than the continental United States, and they can be seen clearly from satellites as huge brown or tan clouds streaming westward over the Atlantic. The journey typically takes 5 to 7 days, with dust particles traveling at altitudes between 15,000 and 20,000 feet. Some of this dust eventually settles on the Caribbean islands, southern United States, and South America, where it provides valuable nutrients to soils. Amazingly, phosphorus in Saharan dust helps fertilize the Amazon rainforest, replacing nutrients washed away by heavy tropical rains, creating a vital intercontinental connection between desert and jungle. However, Saharan dust also has downsides. It can worsen air quality, trigger respiratory problems in sensitive individuals, and may contribute to coral reef die-offs. The dust can also affect hurricane formation by altering atmospheric temperature profiles and potentially inhibiting storm development. This transcontinental movement of dust illustrates how interconnected Earth's systems are, with events in one region directly influencing ecosystems and weather thousands of miles away, or carried on invisible currents of air flowing endlessly around our planet. Some clouds can persist for hours, while others dissipate in minutes. As you lie here, contemplating the sky, you might wonder why some clouds seem permanent fixtures in the atmosphere, while others appear and vanish like ghosts. The lifespan of a cloud depends on many factors, including temperature, humidity, wind patterns, and the availability of moisture. Fair weather cumulus clouds, those puffy white cotton ball clouds of summer afternoons, often have relatively short lives, forming and dissipating over the course of just 10 to 15 minutes. These clouds form when bubbles of warm air rise, cool, and reach their dew point, causing water vapor to condense into visible droplets. If the surrounding air is relatively dry, or if the updraft weakens, the cloud evaporates almost as quickly as it formed. In contrast, large storm systems and the clouds associated with weather fronts can persist for many hours or even days. Stratiform clouds, those flat, layered clouds that create overcast skies, might blanket a region for an entire day or longer because they're fed by steady, widespread lifting of moist air rather than isolated updrafts. The longest-lived cloud formations are often associated with mountain waves, where wind flowing over mountain ranges creates stationary waves in the atmosphere. Lenticular clouds that form in these waves can remain in the same place for hours, looking like flying saucers hovering over peaks, constantly forming on the upwind side as moist air rises and dissipating on the downwind side as air descends, creating the illusion of a stationary cloud. Each cloud is a temporary visible manifestation of invisible atmospheric processes, a brief moment when conditions align perfectly to paint moisture across the sky. The deadliest type of weather is extreme heat, not storms. When we think of dangerous weather, dramatic images often come to mind. Tornadoes tearing through towns, hurricanes flooding coastlines, or blizzards burying entire regions. Yet the weather phenomenon that claims more lives annually worldwide is far quieter and less dramatic: extreme heat. Heat waves kill more people globally than all other weather events combined, though their deadly nature often goes unrecognized because deaths occur gradually and individually rather than in spectacular disasters that make headlines. Extreme heat is particularly dangerous because it puts stress on the human body's cooling mechanisms. When temperatures and humidity are both high, sweat doesn't evaporate efficiently, making it difficult for our bodies to cool themselves. This can lead to heat exhaustion and heat stroke, conditions that can become fatal if not treated promptly. The elderly, young children, people with chronic illnesses, and those without access to air conditioning are especially vulnerable. Urban areas suffer disproportionately because concrete and asphalt absorb heat during the day and release it at night, creating what's called an urban heat island effect that prevents temperatures from dropping enough for people to recover. Heat waves also tend to last for days or weeks, giving the body no respite. In 2003, a severe heat wave across Europe killed an estimated 70,000 people, many of them elderly individuals living alone in homes without air conditioning. As global temperatures rise due to climate change, heat waves are becoming more frequent, more intense, and longer lasting, making this quiet killer an even greater concern for public health officials worldwide. Water can exist in 3 states simultaneously at a specific temperature and pressure. There's a precise point on the temperature and pressure scale where water, ice, and water vapor can all coexist in perfect equilibrium. And this point has a special name, the triple point. For water, this occurs at a temperature of 0.01 degrees Celsius and a pressure of 601.6 pascals, about 0.6% of normal atmospheric pressure at sea level. At this exact combination of conditions, all 3 phases of water, solid ice, liquid water, and gaseous water vapor, can exist together in the same container without any phase dominating the others. The triple point is more than just a curiosity. It's so precise and reproducible that it's used to define the Kelvin temperature scale. Scientists can create triple point cells containing ultra-pure water sealed in glass. And these cells are used as calibration standards for thermometers worldwide. In nature, conditions near the triple point don't occur commonly at Earth's surface, but they can exist briefly in specialized situations or at high altitudes where pressure is low. Understanding phase transitions and the triple point helps meteorologists predict how precipitation will form and fall, whether moisture in clouds will become ice crystals, supercooled water droplets, or remain as vapor. It's a reminder that the simple substance we call water, which seems so familiar, is actually capable of complex and fascinating behavior when conditions are just right, existing simultaneously as ice, liquid, and vapor in a delicate 3-way balance. Tornadoes can have winds exceeding 300 miles per hour. Among nature's most violent and destructive phenomena, tornadoes concentrate tremendous wind speeds into relatively small areas, creating forces capable of obliterating almost anything in their path. The most intense tornadoes, rated EF5 on the enhanced Fujita scale, produce wind speeds estimated at over 200 miles per hour, with some possibly exceeding 300 miles per hour, though measuring winds directly in a tornado is extremely difficult because instruments rarely survive. These violent winds are created by a perfect storm of atmospheric conditions. Strong wind shear, where wind speed or direction changes rapidly with height, abundant moisture in the lower atmosphere, unstable air that wants to rise quickly, and a triggering mechanism like a cold front or dry line to initiate the process. Inside a supercell thunderstorm, Rotating updrafts called mesocyclones can tighten and intensify, eventually extending downward to form a funnel cloud that touches the ground, becoming a tornado. The funnel itself is made visible by condensation and by debris picked up from the ground. Tornadoes vary enormously in size, strength, and behavior. Some are less than 50 feet wide and last only a minute or two, while others stretch more than a mile across and carve paths of destruction for dozens of miles over an hour or more. The largest and longest-lasting tornadoes tend to occur in the central United States during spring months, but tornadoes can form anywhere in the world given the right conditions. These spinning vortices of wind represent nature's power, concentrated into an almost impossibly tight space, a reminder of the immense energies constantly flowing through our atmosphere. Cold air is denser and heavier than warm air. The simple fact that cold air is heavier than warm air drives most of the weather patterns we experience, from gentle breezes to violent storms. Air molecules move more slowly when cold, allowing them to pack closer together, increasing density. When air is warm, molecules move faster and spread farther apart, decreasing density. This difference might seem trivial, but it creates pressure differences that set air in motion. Cold, dense air sinks, while warm, less dense air rises, creating vertical circulation patterns called convection. On a small scale, this is why your ceiling is warmer than your floor. On a planetary scale, this same principle drives trade winds, monsoons, and the jet stream. When a mass of cold air meets a mass of warm air, the cold air slides underneath like a wedge, forcing the warm air upward. If the warm air is moist, this lifting can trigger clouds and precipitation, creating the weather fronts that sweep across continents. In mountainous terrain, cold air drainage creates distinctive patterns. At night, cold air flows downhill like an invisible river, pooling in valleys and basins where it can create frost pockets, even when surrounding hillsides remain frost-free. This density difference is also why hot air balloons work. The heated air inside the balloon is less dense than the cool air outside, providing buoyancy that lifts the balloon upward. Every weather phenomenon, from the gentlest breeze to the most powerful hurricane, ultimately traces back to this simple principle. Temperature differences create density differences. Density differences create pressure differences. And pressure differences set air in motion, painting our skies with endless patterns of clouds and storms. Snowflakes all have 6 sides, but no two are exactly alike. The phrase "no two snowflakes are alike" has become a cliché, a metaphor for uniqueness. Yet it's scientifically accurate and deeply fascinating. Every snowflake begins as a tiny ice crystal forming around a nucleus, perhaps a speck of dust or pollen. As the crystal falls through clouds, water vapor freezes onto its surface, building up layer by layer. The temperature and humidity the crystal encounters during its descent determine how it grows. And since each snowflake follows a slightly different path through slightly different conditions, each one develops a unique pattern. The hexagonal structure comes from the molecular geometry of water. When water molecules freeze, they bond at specific angles, naturally creating 6-fold symmetry. This is why virtually all snowflakes have 6 sides or 6 arms. But within this constraint, infinite variations emerge. Depending on temperature, humidity, and other factors, snowflakes can form as simple hexagonal plates as stellar dendrites with elaborate branching arms, as needles, as columns, or as combinations of these forms. Some are plain and geometric, others extraordinarily intricate and delicate. At temperatures just below freezing, around 27 to 32 degrees Fahrenheit, thin hexagonal plates tend to form. Around 5 to 10 degrees Fahrenheit, the iconic branching stellar crystals develop. Colder still, simple columns dominate. A snowflake, falling through varying temperature layers, might show features from multiple forms, recording its journey like a frozen diary. While it's theoretically possible that two simple snowflakes might be identical, the odds of two complex dendrite snowflakes being atom for atom identical are essentially zero, making each one a tiny miracle of crystalline art. The jet stream flows at speeds up to 250 miles per hour, high above the weather that affects our daily lives, between 6 and 9 miles above Earth's surface. Rivers of air race around the planet at tremendous speeds. These are the jet streams, narrow bands of strong wind flowing from west to east in both hemispheres. The polar jet streams, located at mid-latitudes, are created by the temperature contrast between cold polar air and warm tropical air. Where these air masses meet, pressure differences generate powerful winds that increase with altitude. In winter, when the temperature contrast is greatest, the polar jet stream strengthens and can reach speeds of 200 to 250 miles per hour, as fast as a commercial airliner. Pilots know these winds well. Flying with the jet stream can cut hours off a trip from west to east, while flying against it lengthens the journey and burns more fuel. The jet stream isn't stationary. It meanders north and south, creating large waves and loops called Rossby waves. These meanders help transport heat from the tropics toward the poles and cold air toward the equator, moderating temperature extremes. The jet stream's position and intensity also influence where storms develop and track. When the jet stream dips far south, it can bring cold Arctic air and storms to regions that are normally mild. When it retreats north, warm air surges poleward. In recent years, scientists have observed that the jet stream is becoming wavier and slower, possibly due to Arctic warming, which reduces the temperature gradient that drives it. These changes may be contributing to more persistent weather patterns, both favorable and extreme, staying in place for extended periods rather than moving on quickly. Virga is rain that evaporates before reaching the ground. On hot, dry days, particularly in arid regions, you might look up and see what appears to be rain falling from clouds, trailing downward in visible streaks or wisps. Yet nothing reaches the ground, and the pavement beneath these clouds remains completely dry. This phenomenon is called virga, from a Latin word meaning twig or branch, describing the appearance of these precipitation trails. Virga forms when rain or ice crystals fall from clouds into a layer of very dry air beneath. As the precipitation descends, it evaporates, the water returning to vapor before completing its journey to the surface. The visible streaks you see are the falling droplets or crystals scattering light. Sometimes virga appears as delicate, hair-like strands hanging from the base of a cloud. Other times it creates a more dramatic curtain effect, especially when viewed from a distance at sunset, when low-angle light illuminates the falling precipitation. Virga is particularly common in deserts and semi-arid regions, where surface heating creates a deep layer of hot, dry air. Even in humid climates, Virga can occur when a dry layer exists at mid-levels of the atmosphere. While Virga doesn't deliver moisture to the ground, it does cool and moisten the air it falls through. In some cases, this can contribute to creating or strengthening downdrafts, gusts of sinking air that spread out when they reach the surface, potentially creating dust storms or outflow boundaries that trigger new thunderstorms. Virga is a beautiful reminder that precipitation is a journey, not always completed, and that the atmosphere has layers with vastly different properties. Hurricane winds rotate counterclockwise in the northern hemisphere. The way hurricanes spin is not random, but follows a predictable pattern determined by Earth's rotation. In the northern hemisphere, hurricanes rotate counterclockwise when viewed from above, while in the southern hemisphere, they rotate clockwise. This occurs because of the Coriolis effect, a consequence of Earth spinning on its axis. As air rushes toward a low-pressure system, the Coriolis force deflects it to the right in the northern hemisphere, creating counterclockwise rotation. The opposite deflection occurs south of the equator. Interestingly, hurricanes almost never form directly at the equator, within about 5 degrees of latitude north or south, because the Coriolis effect is too weak there to initiate rotation. The rotation in a hurricane is essential to its structure and intensity. As air spirals inward toward the center, conservation of angular momentum causes it to spin faster, similar to how figure skaters spin faster when they pull their arms in. This creates the eye of the hurricane, a relatively calm area of low pressure at the center, surrounded by the eye wall, where the strongest winds and heaviest rain occur. The rotation also helps hurricanes maintain their structure and tap into the energy released when water vapor condenses into clouds. Snowflakes all have 6 sides, but no two are exactly alike. The phrase, "no two snowflakes are alike," has become a cliché, a metaphor for uniqueness, yet it's scientifically accurate and deeply fascinating. Every snowflake begins as a tiny ice crystal forming around a nucleus, perhaps a speck of dust or pollen. As the crystal falls through clouds, water vapor freezes onto its surface, building up layer by layer. The temperature and humidity the crystal encounters during its descent determine how it grows. And since each snowflake follows a slightly different path through slightly different conditions, each one develops a unique pattern. The hexagonal structure comes from the molecular geometry of water. When water molecules freeze, they bond at specific angles, naturally creating 6-fold symmetry. This is why virtually all snowflakes have 6 sides or 6 arms. But within this constraint, infinite variations emerge. Depending on temperature, humidity, and other factors, snowflakes can form as simple hexagonal plates, as stellar dendrites with elaborate branching arms, as needles, as columns, or as combinations of these forms. Some are plain and geometric, others extraordinarily intricate and delicate. At temperatures just below freezing, around 27 to 32 degrees Fahrenheit, thin hexagonal plates tend to form. Around 5 to 10 degrees Fahrenheit, the iconic branching stellar crystals develop. Colder still, simple columns dominate. A snowflake, falling through varying temperature layers, might show features from multiple forms, recording its journey like a frozen diary. While it's theoretically possible that 2 simple snowflakes might be identical, the odds of 2 complex dendrite snowflakes being atom for atom identical are essentially 0, making each one a tiny miracle of crystalline art. The jet stream flows at speeds up to 250 miles per hour, high above the weather that affects our daily lives, between 6 and 9 miles above Earth's surface. Rivers of air race around the planet at tremendous speeds. These are the jet streams, narrow bands of strong wind flowing from west to east in both hemispheres. The polar jet streams, located at mid-latitudes, are created by the temperature contrast between cold polar air and warm tropical air. Where these air masses meet, pressure differences generate powerful winds that increase with altitude. In winter, when the temperature contrast is greatest, the polar jet stream strengthens and can reach speeds of 200 to 250 miles per hour, as fast as a commercial airliner. Pilots know these winds well. Flying with the jet stream can cut hours off a trip from west to east, while flying against it lengthens the journey and burns more fuel. The jet stream isn't stationary. It meanders north and south, creating large waves and loops called Rossby waves. These meanders help transport heat from the tropics toward the poles and cold air toward the equator, moderating temperature extremes. The jet stream's position and intensity also influence where storms develop and track. When the jet stream dips far south, it can bring cold Arctic air and storms to regions that are normally mild. When it retreats north, warm air surges poleward. In recent years, scientists have observed that the jet stream is becoming wavier and slower, possibly due to Arctic warming, which reduces the temperature gradient that drives it. These changes may be contributing to more persistent weather patterns, both favorable and extreme, staying in place for extended periods rather than moving on quickly. Virga is rain that evaporates before reaching the ground. On hot, dry days, particularly in arid regions, you might look up and see what appears to be rain falling from clouds, trailing downward in visible streaks or wisps. Yet nothing reaches the ground, and the pavement beneath these clouds remains completely dry. This phenomenon is called virga, from a Latin word meaning twig or branch, describing the appearance of these precipitation trails. Virga forms when rain or ice crystals fall from clouds into a layer of very dry air beneath. As the precipitation descends, it evaporates, the water returning to vapor before completing its journey to the surface. The visible streaks you see are the falling droplets or crystals scattering light. Sometimes virga appears as delicate, hair-like strands hanging from the base of a cloud. Other times it creates a more dramatic curtain effect, especially when viewed from a distance at sunset, when low-angle light illuminates the falling precipitation. Virga is particularly common in deserts and semi-arid regions, where surface heating creates a deep layer of hot, dry air. Even in humid climates, virga can occur when a dry layer exists at mid-levels of the atmosphere. While virga doesn't deliver moisture to the ground, it does cool and moisten the air it falls through. In some cases, this can contribute to creating or strengthening downdrafts, gusts of sinking air that spread out when they reach the surface, potentially creating dust storms or outflow boundaries that trigger new thunderstorms. Virga is a beautiful reminder that precipitation is a journey, not always completed, and that the atmosphere has layers with vastly different properties. Hurricane winds rotate counterclockwise in the northern hemisphere. The way hurricanes spin is not random, but follows a predictable pattern determined by Earth's rotation. In the northern hemisphere, hurricanes rotate counterclockwise when viewed from above, while in the southern hemisphere, they rotate clockwise. This occurs because of the Coriolis effect, a consequence of Earth spinning on its axis. As air rushes toward a low-pressure system, the Coriolis force deflects it to the right in the northern hemisphere, creating counterclockwise rotation. The opposite deflection occurs south of the equator. Interestingly, hurricane is almost never formed directly at the equator, within about 5 degrees of latitude north or south, because the Coriolis effect is too weak there to initiate rotation. The rotation in a hurricane is essential to its structure and intensity. As air spirals inward toward the center, conservation of angular momentum causes it to spin faster, similar to how figure skaters spin faster when they pull their arms in. This creates the eye of the hurricane, a relatively calm area of low pressure at the center, surrounded by the eye wall, where the strongest winds and heaviest rain occur. The rotation also helps hurricanes maintain their structure and tap into the energy released when water vapor condenses into clouds. Without rotation, the heat and moisture feeding the storm would quickly spread out and dissipate. The spinning vortex concentrates energy, allowing hurricanes to intensify into nature's most powerful storms, sustained by warm ocean water and capable of producing winds exceeding 150 miles per hour in the most intense examples. Understanding hurricane rotation helps meteorologists predict their behavior and warn communities in their path. A single lightning bolt can carry up to 1 billion volts. The electrical discharge we call lightning is one of nature's most powerful and awe-inspiring displays of energy. A typical lightning bolt carries a current of about 30,000 amperes and can have voltages reaching up to 1 billion volts, though most lightning operates in the 100 million to 300 million volt range. For comparison, household electricity is typically 120 volts. The channel through which lightning travels heats the air to approximately 50,000 degrees Fahrenheit, roughly 5 times hotter than the surface of the sun. This extreme heating causes the air to expand explosively, creating the shock wave we hear as thunder. Light travels much faster than sound, which is why we see the lightning flash before hearing the thunder. You can estimate how far away lightning struck by counting the seconds between flash and thunder, then dividing by 5 to get the approximate distance in miles. Lightning forms through a complex process involving ice crystals colliding in clouds, creating a separation of electric charge. Typically, positive charges accumulate near the cloud top, while negative charges concentrate toward the bottom. When the charge difference becomes large enough, it overcomes air's natural resistance to electrical flow, and a channel of ionized air forms, allowing current to flow. Most lightning discharges occur within clouds or between clouds, but about 20% reaches the ground. These cloud-to-ground strikes begin with a nearly invisible, stepped leader feeling its way downward in a branching pattern. When it nears the ground, a return stroke races back up the channel, carrying most of the current and creating the bright flash we see. Some lightning bolts consist of multiple strokes following the same channel in rapid succession, making the lightning appear to flicker. Deserts can get extremely cold at night. The popular image of a desert is a land of scorching heat, endless sand dunes baking under a merciless sun. While deserts do experience extreme heat during the day, they can also become surprisingly cold at night, sometimes even dropping below freezing. This dramatic temperature swing occurs because deserts lack moisture and vegetation. During the day, the sun's energy heats the ground intensely, and with little vegetation to provide shade, temperatures can soar well above 100 degrees Fahrenheit. However, water vapor is the atmosphere's most important greenhouse gas. Ball lightning is a rare and poorly understood phenomenon. Among weather phenomena, few are as mysterious and controversial as ball lightning. Witnesses describe seeing glowing spheres, typically the size of a grapefruit or basketball, floating or moving slowly through the air, often during or shortly after thunderstorms. These spheres allegedly last from a few seconds to several minutes before fading away or sometimes exploding. Reports describe them passing through walls and windows, moving independently of wind, and occasionally causing damage. Despite thousands of reported sightings over centuries, ball lightning has rarely been photographed or measured scientifically, leading some skeptics to question whether it exists at all. However, enough credible reports exist from trained observers, including pilots, scientists, and weather professionals, that most researchers believe ball lightning is real, even if we don't fully understand it. Various theories attempt to explain ball lightning. Some suggest it's a plasma, ionized gas, sustained by electromagnetic fields from the thunderstorm. Others propose it might be chemical reactions involving vaporized silicon from soil struck by lightning. Recent laboratory experiments have created glowing orbs that somewhat resemble reported ball lightning, using high-voltage discharges and various materials, suggesting multiple mechanisms might be at work. The rarity and unpredictability of ball lightning makes it extremely difficult to study. Scientists can't create it reliably in laboratories or predict when and where it will appear in nature. This mystery reminds us that despite centuries of studying weather and electricity, nature still harbors phenomena that elude our complete understanding, keeping alive a sense of wonder about the world around us. The coldest temperature ever recorded on Earth was -128.6 degrees Fahrenheit. Antarctica, Earth's most remote and hostile continent, holds the record for the coldest temperature ever reliably measured on our planet's surface. On July 21st, 1983, at the Soviet Vostok station in East Antarctica, thermometers registered -128.6 degrees Fahrenheit, or -89.2 degrees Celsius. This bone-chilling measurement occurred during the Antarctic winter, when the sun doesn't rise above the horizon for months, allowing temperatures to plummet to almost unimaginable lows. East Antarctica's high elevation, over 2 miles above sea level at Vostok, combined with the continent's ice-covered surface, which reflects sunlight rather than absorbing it, and its extreme dryness, create perfect conditions for record cold. More recent satellite measurements have detected even lower temperatures in East Antarctic hollows and valleys, with readings as low as -144 degrees Fahrenheit or -98 degrees Celsius. However, these satellite readings measure snow surface temperature rather than air temperature, so they're considered a different category of record. At temperatures this extreme, the environment becomes surreal and alien. Exposed skin freezes in seconds. Any moisture in your breath instantly crystallizes into ice crystals. Metals become brittle and can shatter. Rubber and plastic materials crack and break. Even special polar-grade equipment struggles to function. Scientists working at these temperatures must take extraordinary precautions, limiting outdoor exposure and using specially designed heated shelters and equipment. For comparison, the coldest temperature naturally occurring on Mars is about -195 degrees Fahrenheit, meaning Antarctica's record cold is actually more than halfway to Martian conditions, a reminder of the extreme range of conditions present even on our relatively temperate planet. some locations experience white rainbows called fog bows. In the family of optical phenomena created by water droplets and light, fog bows are among the most subtle and ethereal. Like rainbows, fog bows form when sunlight interacts with water droplets in the air. But while rainbows require relatively large raindrops and produce vivid colors, fog bows form in fog or cloud, where droplets are much smaller, typically less than 50 micrometers in diameter. These tiny droplets diffract light differently than large raindrops, causing the colors to overlap and blend rather than separate into distinct bands. The result is an arc that appears white or very pale, sometimes with faint hints of color at the edges. Blues and reds may be barely visible at the outer and inner boundaries. The fog bow arc follows the same basic geometry as a rainbow, appearing as a bow opposite the sun at around 42 degrees from the anti-solar point. However, fog bows are usually much broader and more diffuse than rainbows, creating a wide, ghostly band of white light. They're most commonly seen in thin fog or cloud when the sun breaks through, particularly in mountains where you might be above cloud layers, or in coastal areas with sea fog. The center of a fog bow's arc, the area inside the bow, often appears noticeably brighter than the surrounding fog, an effect called Heiligenschein, or glory. Sometimes smaller, colored rings called a glory can appear within or alongside a fog bow, created by light that has passed through and backscattered by the fog droplets. Observing a fog bow is a peaceful, almost magical experience, a reminder that optics and water can paint the air with light in countless subtle ways beyond the familiar rainbow. Mountains create their own weather patterns. If you've ever hiked in mountains, you've probably noticed how weather can change dramatically over short distances. Mountains don't merely experience weather. They actively create it through their interaction with air masses and atmospheric circulation. When wind encounters a mountain range, the air is forced upward. As it rises, it expands and cools, and if the air is moist enough, cooling causes water vapor to condense into clouds and precipitation. This is called orographic lifting, and it's why mountain windward slopes often receive heavy rainfall or snowfall, while leeward slopes remain dry, creating what's called a rain shadow. The Cascade Range in Washington and Oregon demonstrates this perfectly. The western slopes receive over 100 inches of precipitation annually, creating lush, temperate rainforests, while areas east of the mountains receive less than 10 inches, creating semi-desert conditions. Mountains also create localized wind patterns. During the day, sun-heated slopes warm the air above them, creating upslope winds as the warmed air rises. At night, the process reverses. Slopes cool rapidly, chilling the air, which becomes denser and flows downhill as mountain breezes. Valley fog and frost are often results of this cold air drainage pooling in low areas. In some locations, strong winds called föhn winds or Chinook winds form when air is forced over mountains, then descends rapidly on the other side, warming and drying as it sinks. These winds can raise temperatures dramatically in just hours, melting snow and creating extreme fire danger. Mountain peaks also pierce into different atmospheric layers, experiencing stronger winds and colder temperatures than surrounding lowlands. This is why mountains often wear clouds like hats. The summits reach up into layers where moisture condenses, even when valleys below remain clear. Cirrus clouds are made entirely of ice crystals, high above the landscape, often at altitudes of 20,000 to 45,000 feet, delicate wisps of clouds streak across the sky. These are cirrus clouds. And unlike the water droplet clouds that form at lower altitudes, cirrus clouds consist entirely of tiny ice crystals. At the extreme cold of high altitude, water vapor skips the liquid phase and crystallizes directly into ice, a process called deposition. The ice crystals in cirrus clouds are typically quite small, but they're large enough to fall slowly through the thin air. As they fall, they often trail downward in distinctive wispy patterns called fall streaks or mare's tails, creating the characteristic feathery appearance of cirrus clouds. Strong winds at high altitude, often part of the jet stream, can stretch cirrus clouds into long linear bands that mark the flow of upper-level winds. Because cirrus clouds contain ice rather than water droplets, they interact with sunlight differently than lower clouds. They're semi-transparent, allowing sunlight to pass through while scattering and refracting light, sometimes creating beautiful optical phenomena called halos, rings of light around the sun or moon. These halos form when sunlight passes through the hexagonal ice crystals at specific angles, similar to how raindrops create rainbows. Meteorologists pay attention to cirrus clouds because they often signal approaching weather changes. Cirrus clouds frequently precede warm fronts and storms by 12 to 24 hours, as the high-altitude moisture associated with approaching systems arrives first. Thickening and lowering cirrus clouds typically indicate that rain or snow is on the way. These high, icy clouds also play a role in Earth's energy balance, both reflecting some sunlight back to space and trapping some heat radiating from below, making them important players in climate science. The lowest air pressure ever recorded was 870 millibars. Atmospheric pressure, the weight of air pressing down on Earth's surface, varies constantly as weather systems move and evolve, but it typically stays within a fairly narrow range around 1013 millibars, or 29.92 inches of mercury at sea level. However, inside the most intense tropical cyclones, pressure can drop to astonishing lows. The record belongs to Typhoon Tip, which formed in the western Pacific Ocean in October 1979. At its peak intensity, the pressure at Tip's center dropped to just 870 millibars, or 25.69 inches of mercury, the lowest sea level pressure ever reliably recorded on Earth. This represented a pressure difference of over 140 millibars compared to normal atmospheric pressure. Such extreme low pressure is both a cause and effect of a hurricane's strength. As air converges toward the low pressure center and rises, it accelerates, creating stronger winds. These winds bring more moisture and energy into the storm, further intensifying the low pressure. Typhoon Tip was also the largest tropical cyclone on record, with tropical storm force winds extending 150 miles across, an area larger than the continental United States. Wind speeds in Tip reached 190 miles per hour. The storm caused significant damage and loss of life, despite weakening before making landfall in Japan. Understanding how storms reach such extreme intensities helps meteorologists predict dangerous tropical cyclones and improve warnings. These record-breaking storms remind us that the atmosphere can create pressure gradients and wind speeds that challenge human infrastructure and demand respect for nature's power. Some clouds glow at night, called noctilucent clouds. On rare summer nights in high-latitude regions, a ghostly glow sometimes appears in the twilight sky, hours after sunset or before sunrise. These are noctilucent clouds, literally night-shining clouds, and they're among the highest and most unusual cloud formations on Earth. Unlike normal clouds that form in the troposphere below about 10 miles altitude, Noctilucent clouds form in the mesosphere at altitudes of 47 to 53 miles, far above where ordinary weather occurs. At these extreme heights, temperatures can drop below minus 180 degrees Fahrenheit, cold enough for water vapor to freeze even in the incredibly thin air. The clouds form when tiny ice crystals, possibly nucleated on meteor dust particles, grow large enough to scatter sunlight. They're only visible during twilight, when the sun is below the horizon from your perspective, but still illuminating these extremely high clouds from below. The observer on the ground sees them glowing electric blue or silvery white against the darkening sky, while lower clouds are in shadow. Noctilucent clouds were rarely reported before the late 19th century, leading scientists to wonder if they're a relatively recent phenomenon, possibly connected to industrial activity or climate change. Some research suggests that increasing methane in the atmosphere could be adding water vapor to the mesosphere, making these clouds more common. They're most frequently observed between 50 and 70 degrees latitude during summer months when mesospheric temperatures are coldest. The clouds often display intricate ripple patterns and wave structures, revealing invisible atmospheric dynamics in this remote layer of our atmosphere. Witnessing noctilucent clouds is a rare treat, offering a glimpse of weather occurring at the very edge of space. Wind chill can make temperature feel much colder than it actually is. On a bitterly cold winter day, weather forecasts often mention wind chill in addition to actual temperature, and the wind chill value is usually significantly colder. Wind chill isn't just a matter of perception. It represents the real rate at which your body loses heat in cold, windy conditions. When air is calm, your body heats a thin layer of air next to your skin, creating insulation. But when wind blows, it constantly replaces this warm layer with cold air, accelerating heat loss. Wind chill calculations estimate how cold the air feels on exposed skin by factoring in both temperature and wind speed. For example, if the actual temperature is 0 degrees Fahrenheit and wind is blowing at 15 miles per hour, the wind chill makes it feel like minus 19 degrees. In and out, these conditions, frostbite, can occur on exposed skin in about 30 minutes. The faster the wind blows, the more dramatic the effect, though the relationship isn't linear. Wind chill impact increases most dramatically at moderate wind speeds, then levels off. Extremely high winds don't produce proportionally more cooling, because at a certain point, the warm air layer is being stripped away as fast as physics allows. It's important to note that wind chill only affects living things and objects that generate heat, like humans and animals. Inanimate objects like car engines or water pipes cool to the actual air temperature, not the wind chill temperature, though strong winds may help them reach that temperature faster. Understanding wind chill is crucial for winter safety, helping people prepare appropriately for cold weather and avoid frostbite or hypothermia. The wind chill concept, while useful, doesn't apply when temperatures are at or above 50 degrees Fahrenheit, because heat loss isn't concerning at those temperatures. Clouds can weigh millions of pounds, yet float effortlessly. Looking up at clouds drifting peacefully across a summer sky, it's almost impossible to imagine that these soft, ethereal forms are actually extraordinarily heavy. A typical cumulus cloud, one of those puffy white clouds that look like cotton balls, contains roughly 500,000 pounds of water distributed throughout its volume as tiny droplets. Larger clouds contain even more. A mature thunderstorm cloud can hold millions of pounds of water. So why don't these clouds crash down on us? The answer lies in the size of the water droplets and the motion of air within clouds. The water in clouds exists as extremely small droplets, typically 10 to 20 micrometers in diameter, much smaller than the period at the end of this sentence. At this size, droplets fall very slowly through air, just a centimeter per second or so, because air resistance is strong relative to their tiny mass. Meanwhile, updrafts within and around the cloud, rising currents of warm air, often move upward faster than the droplets fall, keeping them suspended. Additionally, the cloud's total weight is distributed across an enormous volume. A medium-sized cumulus cloud might measure half a mile wide, half a mile tall, and half a mile deep, giving it a volume of about 1.2 cubic miles. Spread the cloud's weight across this vast space, and the density is actually lower than the surrounding air, which is why clouds float. This counterintuitive fact demonstrates one of nature's elegant balances. The same physical principles that make clouds impossible to hold also allow them to be beautiful, temporary sculptures in the sky, constantly forming, changing, and dissipating in an endless cycle of evaporation and condensation. Antarctica contains about 90% of Earth's ice and 70% of its fresh water. When we think of freshwater resources, we typically picture rivers, lakes, and underground aquifers. But by far, the largest reservoir of fresh water on Earth exists in a place where almost nobody lives, and water is locked in solid form: Antarctica. This frozen continent, larger than the United States and Mexico combined, holds approximately 6.4 million cubic miles of ice, representing about 90% of all ice on Earth, and roughly 70% of the planet's fresh water. If all of Antarctica's ice melted, global sea levels would rise about 200 feet, enough to submerge most coastal cities worldwide. The ice sheet covering Antarctica isn't just thick. In some places, it exceeds 2.5 miles in depth, burying entire mountain ranges. Only the tallest peaks poke above the ice surface. This massive ice sheet formed over millions of years as snow accumulated layer upon layer, compressing older snow into dense ice that flows very slowly outward from the continent's interior toward the coasts. Despite being the driest continent on Earth in terms of precipitation, most of Antarctica receives less than 2 inches of the precipitation annually, making it technically a desert. The ice continues to accumulate very slowly because temperatures are so cold that almost nothing melts. The ice cores drilled from deep within Antarctica contain trapped air bubbles that preserve atmospheric samples from hundreds of thousands of years ago, providing invaluable records of past climates and helping scientists understand how Earth's climate has changed over time. This frozen archive and vast water reserve reminds us that even Earth's most inhospitable regions play crucial roles in global systems, storing water and preserving climate history in their ancient ice. Humidity doesn't determine if you'll see your breath. On cold mornings, the visible puff of breath we exhale creates a temporary cloud floating before our faces. Many people assume this happens because of humidity in the air, but the real determining factor is temperature, specifically the relationship between the temperature of your exhaled breath and the dew point temperature of the surrounding air. Your breath is warm, typically around 95 degrees Fahrenheit, and it's saturated with moisture from your lungs. When this warm, moist air hits cold outside air, it cools rapidly. If the cold air cools your breath below its dew point, the water vapor condenses into tiny liquid droplets. creating the visible fog you see. This can happen even when the outside air is fairly dry if it's cold enough. Conversely, on a humid but warm day, you won't see your breath because the temperature doesn't drop enough to cause condensation. The threshold temperature, where you start seeing your breath, is typically around 45 degrees Fahrenheit, though this varies depending on the dew point. On very cold days with extremely low humidity, you might see less breath fog than on moderately cold, humid days, because even though your breath cools, there's so little moisture in the surrounding air that condensation is limited. The fog you create with your breath is essentially a cloud you've made yourself, composed of the same water droplets that form natural clouds and fog in the atmosphere. This simple act of breathing on a cold day demonstrates condensation, the same process that creates dew, fog, and clouds, showing us that the same physical principles govern weather phenomena, from the grand scale of storm systems down to the intimate scale of a single breath. The hottest temperature ever reliably recorded was 134 degrees Fahrenheit. On July 10, 1913, in Death Valley, California, thermometers recorded a temperature of 134 degrees Fahrenheit, or 56.7 degrees Celsius, setting a record for the highest reliably measured air temperature on Earth. Death Valley, situated below sea level in California's Mojave Desert, creates conditions perfect for extreme heat. The valley's low elevation means air is compressed and heated by its own weight. Surrounding mountains block cooling ocean breezes and trap heat within the valley. The bare rock and sand surfaces absorb solar radiation intensely and radiate it back, heating the air above. During summer months, Death Valley regularly experiences temperatures exceeding 120 degrees Fahrenheit. At these extreme temperatures, the human body struggles to cool itself. Sweat evaporates almost instantly, carrying heat away from skin, but the body can't produce sweat fast enough to maintain safe core temperature. Exposure to such heat without adequate hydration and cooling can lead to heat exhaustion or fatal heat stroke within hours or even minutes. Even breathing becomes uncomfortable as hot, dry air dries out airways. Some previous temperature records have been discredited under modern scrutiny. A reading of 136 degrees in Libya in 1922 was invalidated due to measurement concerns. Similarly, some extreme readings from the past are viewed skeptically because of equipment limitations and non-standard measurement practices. As global temperatures rise, heat records continue to be approached or broken in various locations. Death Valley itself experienced 129.9 degrees in 2021, pending official verification. Understanding extreme heat and how it forms helps scientists predict dangerous heat waves and protect vulnerable populations as our climate continues warming. Atmospheric rivers carry vast amounts of water vapor. The atmosphere has rivers, not of liquid water like those on the ground, but rivers of water vapor flowing through the sky. These atmospheric rivers are long, narrow bands of concentrated moisture that transport enormous quantities of water vapor from tropical regions toward the poles. A typical atmospheric river can be 250 to 400 miles wide, 1 to 2 miles deep, and over 1,000 miles long, carrying moisture contents comparable to the flow of the Mississippi River at its mouth. Except the water is in vapor form, floating thousands of feet above the surface. These vapor streams form when warm, moist air from tropical oceans gets channeled into narrow bands by atmospheric circulation patterns, particularly jet streams. When an atmospheric river makes landfall on a coastline or mountain range, the moisture is forced upward, cooling and condensing into heavy precipitation. The result can be prolonged, intense rainfall or snowfall that delivers enormous amounts of water in a short time. On the US West Coast, atmospheric rivers are responsible for delivering 30% to 50% of annual precipitation, despite occurring on just a few days each year. California's water supply depends heavily on these events to fill reservoirs and create mountain snowpack. However, atmospheric rivers can also cause destructive flooding, particularly when a series of them strike the same region in quick succession, saturating soil and overwhelming rivers and drainage systems. In extreme cases, atmospheric rivers have deposited 10 to 15 inches of rain in 24 hours across wide areas. Scientists are working to better predict atmospheric rivers and understand how climate change might be affecting their frequency and intensity. Crucial information for water resource management and flood preparation in regions that depend on or are threatened by these vapor rivers in the sky. Haboobs are massive dust storms that create walls of sand. In arid regions with loose, dry soil, thunderstorms can create spectacular and dangerous dust storms called haboobs. The name comes from the Arabic word meaning blasting or drifting, and these storms occur most commonly in desert areas like the Sahara, Middle East, and the southwestern United States, particularly Arizona. A haboob forms when a thunderstorm's downdraft hits the ground and spreads outward as a strong gust front. If the ground is dry and dusty, the rushing wind lifts enormous quantities of dust and sand into the air, creating a rolling wall of dust that can tower thousands of feet high and stretch for dozens or even hundreds of miles wide. The leading edge appears as an ominous, churning brown or tan cloud that advances rapidly, sometimes at speeds exceeding 30 miles per hour, engulfing everything in its path. Visibility drops dramatically, often to near zero, within seconds as the wall arrives. Driving becomes extremely dangerous as the dust wall hits, and numerous vehicle accidents have been caused by people attempting to drive through haboobs. The dust contains fine particles that can penetrate buildings through cracks and vents, coating everything inside with a layer of grit. For people with respiratory conditions, haboobs pose serious health risks. The dust can also carry an organism called coccidioides that causes valley fever, a fungal lung infection. Haboobs typically last from a few minutes to an hour, after which the dust gradually settles. These storms demonstrate how weather phenomena can interact with local geography and surface conditions to create region-specific hazards, transforming a simple thunderstorm outflow into a blinding, choking wall of sand, advancing across the landscape like a solid thing, a reminder of nature's power to reshape and reclaim desert environments. Some places have never recorded measurable rainfall. Among Earth's most extreme environments are hyper-arid deserts, where rain is so rare that weather stations have never recorded measurable precipitation in their entire operational history. Parts of Chile's Atacama Desert, considered the driest place on Earth, fall into this category. Some weather stations there have operated for decades without ever recording rain. The Atacama's extreme aridity results from a combination of factors. It sits in the rain shadow of the Andes Mountains, which block moisture from the Amazon basin to the east. Cold ocean currents offshore create stable atmospheric conditions that suppress cloud formation. And the region lies beneath a persistent high-pressure zone that promotes sinking, drying air. Parts of the Atacama are so dry that NASA uses them as Mars analogues for testing equipment, reasoning that if something can survive Atacama's conditions, it might handle Mars. Despite the lack of rain, some areas receive occasional fog from the Pacific Ocean, allowing specially adapted lichens and cacti to survive by harvesting moisture from the air. Antarctica's dry valleys represent another extreme, with areas that haven't seen rain in over 2 million years according to geological evidence. These valleys receive almost no snow, despite being in Antarctica, because katabatic winds, gravity-driven winds that rush down from the high interior ice sheet, warm as they descend and evaporate any moisture before it can accumulate. The result is bare, frozen soil in the middle of Earth's iciest continent, landscapes that look more alien than terrestrial. These hyper-arid regions teach us that Earth encompasses almost unimaginable diversity of climates, from places drowning in rain to places where rain never falls. Each environment shaped by unique combinations of geography, ocean currents, and atmospheric circulation. Lightning can strike the same place repeatedly. Contrary to the popular saying, lightning definitely can and does strike the same place twice, or many times. Tall structures like skyscrapers, towers, and mountain peaks attract lightning precisely because they're tall, reaching up into the storm's electric field and providing an easier path for electrical discharge than flat ground. The Empire State Building in New York City is struck by lightning an average of 23 times per year. Some communication towers experience dozens of strikes annually. This happens because lightning follows the path of least resistance, and tall objects effectively reduce the distance between the charged cloud and ground, making them preferred targets. Lightning rods work on this principle, providing an intentional, safe path for lightning to follow to the ground rather than striking and potentially damaging the building they protect. Open ground features like lone trees are also lightning magnets, which is why it's extremely dangerous to shelter under a tree during a thunderstorm. In nature, certain geographic locations experience far more lightning than average. Lake Maracaibo in Venezuela holds the record for the most lightning, with storms generating lightning almost 300 nights per year in some areas, earning it the nickname lightning capital of the world. The persistent storms result from moisture from the Caribbean Sea meeting mountain winds at a specific convergence point. The frequency with which lightning strikes the same locations has been harnessed for research. Scientists studying lightning often use towers instrumented with sensors, knowing these towers will be struck repeatedly, allowing data collection. Understanding lightning's preferences helps us design better protection systems and informs building codes in lightning-prone areas, ensuring structures can safely handle repeated strikes over their lifetimes without damage or danger to occupants. The greenhouse effect is essential for life on Earth. When people hear greenhouse effect, they often think only of climate change and global warming. But the natural greenhouse effect is actually essential for making Earth habitable. Without it, our planet would be frozen and lifeless. The greenhouse effect works like this. The sun's energy passes through Earth's atmosphere and warms the surface. The warm surface then radiates heat back towards space. But instead of all escaping, some of this heat is absorbed by greenhouse gases in the atmosphere, primarily water vapor, carbon dioxide, and methane. These gases re-radiate the heat in all directions, including back down toward Earth's surface, effectively trapping heat and keeping our planet warm. Without this natural greenhouse effect, Earth's average temperature would be about 0 degrees Fahrenheit instead of the actual average of about 59 degrees Fahrenheit. The planet would be a frozen ball, unable to sustain liquid water, or complex life. The greenhouse effect is what made Earth suitable for life to evolve and thrive. The problem we face today isn't the greenhouse effect itself, but the enhancement of it through human activities that add extra greenhouse gases to the atmosphere, particularly carbon dioxide from burning fossil fuels. This enhanced greenhouse effect is what drives current climate change, trapping additional heat beyond the natural balance. The distinction is important. The natural greenhouse effect is beneficial and necessary, while the anthropogenic enhancement of it creates imbalances that disrupt climate systems. Understanding this difference helps us appreciate that Earth's atmosphere isn't just empty space, but an active participant in regulating temperature, a delicate blanket that makes the difference between a frozen wasteland and the living, breathing biosphere we call home. Some lightning strikes upward from the ground, while most lightning travels downward from clouds to ground, creating the familiar bright flash we associate with thunderstorms. Some lightning actually travels upward from the ground toward the clouds. These upward moving flashes typically originate from tall structures like communication towers, skyscrapers, or mountain peaks when the electric field near the ground becomes so intense that it initiates an upward moving discharge. Upward lightning is more common from very tall structures, particularly those exceeding 300 or 400 feet, and it's more frequent during winter months for reasons not fully understood. The process begins differently from normal lightning. Rather than a stepped leader coming down from the cloud, upward lightning starts with a positively charged leader shooting upward from the top of a tall structure. If conditions are right, this upward leader connects with negative charge in the cloud, completing the circuit and allowing current to flow. The bright return stroke can then travel either upward or downward depending on the circumstances. From a distance, upward lightning looks similar to cloud-to-ground strikes, but high-speed photography reveals the different initiation mechanism. In some cases, during intense thunderstorms, objects don't even need to be particularly tall for upward strikes to occur, though this is rare. Understanding upward lightning is important for protecting tall structures and the communication equipment they often support. Special lightning protection systems are needed because upward strikes can deliver even more energy than downward strikes to the structure they originate from. This unusual lightning reminds us that electrical discharge during storms is complex, with current flowing both up and down, depending on charge distribution, structure height, and field intensity, creating a complex interplay between Earth and sky. Trade winds blow consistently in tropical regions. In tropical regions, particularly over the oceans, winds blow with remarkable consistency from east to west, a pattern that persists throughout the year with little variation. These are called trade winds, and they were named by sailors who relied on them for transoceanic voyages during the age of sail, trading goods between continents. Trade winds are created by Earth's atmospheric circulation patterns, specifically by Hadley cells. At the equator, intense solar heating causes warm air to rise. This air flows poleward at high altitude, cools, and sinks back to the surface around 30 degrees latitude, north and south, creating subtropical high-pressure zones. From these high-pressure areas, air flows back toward the equator at the surface. But Earth's rotation deflects this flow through the Coriolis effect, turning the winds so they blow from northeast to southwest in the northern hemisphere, and from southeast to northwest in the southern hemisphere. The result is a band of reliable easterly winds in tropical regions. These winds converge near the equator in a zone called the Intertropical Convergence Zone, or ITCZ, where the rising air creates clouds and heavy rainfall. Trade winds are strongest over oceans where friction from the surface is minimal. They average 10 to 15 miles per hour, providing a steady breeze that moderates tropical temperatures and drives ocean currents. The trade winds have profoundly influenced human history, making certain sailing routes possible while rendering others nearly impossible for wooden sailing ships. They helped spread human populations across Pacific islands, enabled European colonization of the Americas, and shaped global commerce patterns. Even today, trade winds influence weather, climate, and ocean conditions in tropical regions, including the development and movement of hurricanes and the periodic disruption of patterns during El Niño events. Frost can form even when air temperature is above freezing. On late autumn or early spring mornings, you might discover frost coating your car windshield or garden plants, even though the thermometer reads several degrees above freezing. This seems impossible at first. How can ice form when temperature is above 32 degrees Fahrenheit? The answer lies in radiative cooling and where temperature is being measured. Standard thermometers measure air temperature at about 5 feet above the ground in a shaded, ventilated enclosure. But objects on the ground can become significantly colder than the air around them through radiative cooling. On clear, calm nights, surfaces like car roofs, grass blades, and leaves radiate heat away to space. If there's no cloud cover to reflect this heat back, and no wind to mix warmer air down to the surface, these surfaces can cool several degrees below the ambient air temperature. When a surface cools below 32 degrees, moisture condenses directly as ice crystals, forming frost, even if the nearby thermometer reads 35 or 36 degrees. This is called a radiation frost. Valleys and low-lying areas are particularly susceptible because cold air drains downhill and pools in these areas, creating even colder conditions. Gardeners know that frost can damage tender plants, even when forecasts predict temperatures just above freezing. So they take protective measures, covering plants, running sprinklers to release latent heat, or using wind machines to mix air to prevent frost damage. Understanding the difference between air temperature and surface temperature helps explain this apparent paradox and reminds us that weather measurements always depend on context. Where, how, and what you're measuring all matter, sometimes making the difference between a frost-free night and a killing frost that ends the growing season. Waterspouts are tornadoes that occur over water. When funnel clouds form over oceans, lakes, or other large bodies of water instead of land, we call them waterspouts rather than tornadoes, though the basic physics is similar. Waterspouts come in two varieties. Fair weather waterspouts are the more common type, forming in relatively calm conditions when cool air moves over warm water. These are generally weaker and shorter lived, with winds typically below 70 miles per hour. They form from the surface upward as rising warm, moist air begins to rotate due to wind shear. Fair weather waterspouts look dramatic, with a funnel extending from cloud base to water surface, often creating a spray ring where the funnel touches the water. Despite their appearance, they rarely pose serious danger to anything except small boats that come too close. Tornadic waterspouts, in contrast, are essentially tornadoes that form over water or move from land to water. These develop from severe thunderstorms and can be just as dangerous as land tornadoes, with similar wind speeds and destructive potential. If a tornadic waterspout moves on shore, it becomes a regular tornado. The funnel appears similar to land tornadoes, but surrounded by water spray instead of dust and debris. Waterspouts are most common in tropical and subtropical regions, particularly the Florida Keys, which experiences hundreds of waterspouts annually. The Mediterranean Sea and the Great Lakes also see frequent waterspouts. Like tornadoes, waterspouts are relatively short-lived, typically lasting from a few minutes to perhaps half an hour. Understanding waterspouts helps mariners and coastal residents recognize danger signs and take appropriate action, whether that's avoiding the area in a boat or seeking shelter if a tornadic waterspout threatens to come ashore. Some clouds produce virga that never reaches the ground. High in the atmosphere, precipitation sometimes falls from clouds in visible streaks or wisps, trailing downward like curtains of grey or white. Yet these streaks fade and disappear before reaching the surface, leaving the ground completely dry. This phenomenon occurs when rain or snow falls into a layer of very dry air below the cloud. As the precipitation descends, it evaporates or sublimates, returning to water vapor before completing its journey to the ground. The visible streaks, called virga, mark falling precipitation that doesn't survive the trip. Virga is particularly common in arid regions where surface heating creates a deep layer of hot, dry air, but it can occur anywhere when dry air exists at mid-levels of the atmosphere. Sometimes virga appears as delicate, hair-like strands hanging from the cloud base. Other times it creates more dramatic curtains, especially when viewed from a distance at sunset, when low-angle sunlight illuminates the falling precipitation. While virga doesn't deliver moisture to the surface, it does affect the atmosphere in important ways. As precipitation evaporates, it cools the air it's falling through and adds moisture to that layer. This evaporative cooling can create or strengthen downdrafts, gusty winds that spread out when they reach the surface. In desert regions, evaporating virga can generate microbursts, localized but powerful downdrafts that spread out violently on hitting the ground, creating brief but intense winds capable of damaging structures and posing serious hazards to aircraft. Virga also affects radar imagery, sometimes appearing as precipitation that weather radar detects, but that never reaches the surface, potentially confusing forecasts. Observing virga reminds us that precipitation is a process rather than a simple event, and that the atmosphere's structure, in layers with different properties, determines whether moisture makes it from cloud to ground. Thunder is caused by the rapid heating of air by lightning. The loud boom and rumble we call thunder is actually a shock wave created by lightning's incredible heat. When a lightning bolt forms, it creates a channel of plasma, ionized air, that reaches temperatures around 50,000 degrees Fahrenheit, roughly 5 times hotter than the surface of the sun. This extreme heating occurs almost instantaneously. In just a fraction of a second, the air in and around the lightning channel explosively expands, creating a shock wave that propagates outward in all directions. This shock wave is what we hear as thunder. The sound begins as a sharp crack or bang when the shock wave passes, then continues as a rumble because different parts of the lightning path are at different distances from the listener. Sound from the nearest section arrives first, followed by sound from more distant sections, creating the characteristic rolling thunder that can last several seconds. Thunder's loudness depends partly on distance. Close lightning creates a sharp, startling crack because the shock wave hasn't had time to dissipate. Distant lightning produces softer rumbling because sound waves spread out and lose. energy as they travel, and also because they bounce off terrain features, clouds and temperature layers in the atmosphere. Since light travels much faster than sound, we see lightning essentially instantly, but hear thunder after a delay. Counting seconds between flash and boom, then dividing by 5, gives the approximate distance to the strike in miles. Thunder typically can't be heard beyond 10 miles or so because the sound waves dissipate or are refracted away by atmospheric conditions. The old saying, "lightning never strikes twice," is false. But the saying, "if you can hear thunder, you're within range of lightning," is wisdom worth remembering during storms. Snow is an excellent insulator, protecting plants and animals. For creatures facing harsh winter conditions, snow is far more than a cold inconvenience. It's a crucial insulator that can mean the difference between survival and death. Fresh snow, particularly powdery snow composed of individual flakes with lots of airspace between them, is an excellent insulator because air trapped between snowflakes is a poor conductor of heat. A deep snowpack creates what's called a subnivean environment, the zone beneath the snow, where small mammals, insects, and plant roots find refuge. Even when air temperature plunges to 0 or below, the space under snow cover might remain near 32 degrees, just at the freezing point of water, because heat from the ground combined with snow's insulation prevents greater temperature drops. Small mammals like voles, shrews, and mice create tunnels and chambers within the snowpack, living out the winter in relative warmth. Plant roots and bulbs beneath the snow are protected from killing cold and desiccating winds that could otherwise freeze and damage them. The insulating properties of snow also benefit human activities. Traditional igloos work precisely because snow is such a good insulator. Thick snow walls keep frigid Arctic winds out, while body heat and small fires keep the interior surprisingly comfortable. Mountain snowpack serves as frozen water storage, slowly melting through spring and summer to feed streams and rivers long after precipitation has ended. However, snow's insulating properties can also create problems. Snow covering roads insulates the pavement beneath, potentially keeping it above freezing even when air temperature drops. But if compacted snow forms ice, that ice is then insulated from warming sunshine and can persist for extended periods. Understanding snow as an insulator helps us appreciate that winter landscapes aren't simply frozen and dead, but harboring hidden worlds of protected life waiting for spring. The Coriolis effect influences more than just weather. Earth's rotation creates an apparent force, called the Coriolis effect, that deflects moving objects to the right in the northern hemisphere and to the left in the southern hemisphere. Most people learn about the Coriolis effect in the context of weather, how it causes hurricanes to rotate counterclockwise in the north and clockwise in the south, and how it steers wind patterns. But this effect influences many other phenomena. Ocean currents are strongly affected by the Coriolis effect, creating rotating gyres in ocean basins. Aircraft and missiles traveling long distances must account for Coriolis deflection in their navigation. Even artillery shells fired over long distances can miss their targets if the Coriolis effect isn't factored into calculations. The effect is proportional to the object's speed and the sign of latitude, meaning it's strongest at the poles, weak near the equator, and more pronounced for fast-moving objects. Contrary to popular myth, the Coriolis effect does not determine which way water drains from bathtubs or toilets. This happens too quickly, at too small a scale for the Coriolis effect to matter. Basin shape and water entry angle dominate those situations. But for large-scale, long-duration movements in Earth's fluid envelopes, air and water, the Coriolis effect is crucial. It's a reminder that we live on a rotating planet, and this rotation has subtle but pervasive effects on how things move across Earth's surface. The mathematics of the Coriolis effect aren't intuitive, which is why it took scientists until the 19th century to fully understand and describe it, despite obvious observations like hurricane rotation being known far longer. Even today, visualizing and understanding the Coriolis effect challenges students, a testament to how our everyday experience on a rotating sphere doesn't prepare our intuition for the consequences of that rotation. As our journey through the atmosphere comes to a gentle close, let the vast knowledge of weather systems and natural phenomena settle softly in your mind, like morning dew on grass. Remember that every breath you take connects you to these global patterns, to winds that circle the planet and water that cycles endlessly between ocean and sky. The weather continues its eternal dance, whether we observe it or not, painting our skies with clouds, feeding our rivers with rain, and shaping the very landscapes we call home. May the rhythm of these atmospheric processes, as constant and reliable as Earth's rotation, carry you peacefully into deep, restorative sleep. Thank you for joining me on this calming exploration of weather's wonders. If you enjoyed this journey through our atmosphere, please consider liking and subscribing to the Cozy Curiosity channel, where curiosity meets calm every night. Sleep well, stay curious, and until next time, let the gentle winds of knowledge carry you peacefully through the night.